going to take over and talk to us about galactic archeology.
So I'll start off with a little joke that has to do with the name of my talk. When you're a grad student, you get opportunities to go to conferences, go places to collect data, so you end up finding yourself on an airplane, and of course, when you're on a plane, you're going to be sit down next to a stranger, and you know they always like to try to make polite conversation with you, right? So and one of the first questions that always comes up is, what do you do? So I would give an answer that had everything to do with how interested I was in actually having a conversation. And so if I was not at all interested, I would say, oh, I'm an astrophysicist, because everybody kind of has a inkling of what that means, but they don't really know, so that usually kind of cuts it off. I might say I was a physicist. If I wanted to have a conversation, I'd say something like I'm an astronomer, or if I was feeling really talkative, I would say I'm a galactic archaeologist, because that just begs for all kinds of explanation of what that could mean. So galactic archaeology is kind of a whimsical term for a particular subfield within astronomy, and it turns out to be that's the subfield that I did my PhD thesis within. So my goal in 30 minutes is to basically give you a quick overview of the field, and then a taste of what I did in my actual dissertation. So it's kind of a tall order. We'll be moving pretty quick, and hopefully I don't lose everyone. So if you have a question, raise your hand, and I'm happy to answer questions as we go along. And then, of course, at the end, we're going to have a Q&A session then as well. So let's get going. So the first thing I want to say, because I'm not sure, the people in here are astronomy club and astronomy majors, but just to make sure that nobody gets out of here without knowing this, we live within a galaxy, and we call that galaxy the Milky Way. And when we look up at the night sky, this is what it looks like. It's a kind of diffuse band that goes across the sky. This particular picture was taken in Chile, this observatory, and this line right here is pointing you towards where the galactic center is. So it's a very beautiful thing, and most people have some. If you're lucky and you get to go to a dark sky site, then you get to see this wonderful thing. Here in Atlanta, the sky's too bright to see it, but hopefully one day you'll be so lucky to see something like that in person. Studying the structure of those stars, where they're laid out in the sky, how far they are, where they're at, we can piece together a picture of what our galaxy looks like. Even though we're living within it, this is an artist's representation of what our galaxy probably would look like if we were above looking down on it. So the basic structure here is we have a central bulge. It's kind of elongated with a bar. We call this the galactic bar. That's going to be very important in my talk, talking about the galactic bar. There are spiral arms coming out, so we say that we're in a spiral galaxy. And we live out on one of the arms down here. It's probably hard to see because of the lights, but the sun is down here about 2/3 of the way out in one of the arms. So what is galactic archaeology? It's the astronomers that work on trying to look at the stars in our Milky Way, how they are now, and trying to piece together how things have changed over time. So piecing together the history of the Milky Way galaxy. So in a way, archaeology is kind of the wrong word. It would probably be more correct to say galactic paleontology, but galactic archaeology is a term that appears in the literature, so that's what I'm using here. So basically, there's two kinds of information that you usually see people taking advantage of in order to do this kind of work. It's what we call the kinematics of stars, so it's how are the stars moving in the Milky Way, and it's the compositions of the stars, in other words, what they're made of. Other things that we would also like to use include the age of stars, but it turns out the age of stars, individual stars, which is what we're working with in this field, is very difficult to determine. So these are the two things we can measure pretty well that we can use to try to answer our questions. The kinematics, how they move, and the composition, what are they made of. So why is the kinematics useful? Well, we can, by looking at how the stars move, we can find that there's different groups of stars that are moving in specific kinds of ways. So we can take our pretty, the pretty picture of the Milky Way looking down from above, we can break that up into some basic components of what the components of our Milky Way galaxy are. We have this large spherical component that we call the halo. This actually is a small component in terms of the number of stars. Most of the stars live down here in the disk. We have two components to the disk, what we call the thin disk. That's where the sun lives, where the sun is a thin disk star. And then there's another component to the disk called the thick disk, and then down by the galactic center is the bulge. The halo and the bulge are both spherical. They're both old stars, but they have different compositions. The thick disk and the thin disk have similar compositions, but we can actually see there's some differences. Did you have a question? I wasn't sure. Raise your hand. I don't know. Where was I? Okay, so the thin and the thick disk stars have different orbits and slightly different compositions. There's actually ongoing research in this area about what is the connection between the thick disk and the thin disk. So with the kinematics, we can divide stars into groups, stars which are moving similarly. And so it might be natural to think that stars that are all kind of moving together might all be related somehow. It's just kind of that's the first thing to do. This is kind of a new field. Well, it's a new field in one sense. We break stars up into groups according to how they're moving, and then we use other methods to test if those groups are sensible. So the picture that I showed you a second ago had this very regular picture showing how the halo was just a nice spherical ball enveloping our galaxy. But consider this picture. This is, when I was doing my PhD dissertation, this was my favorite picture. This is a picture from the Sloan Digital Sky Survey where they pointed their telescope at a part of the sky that's not including the disk. So we're looking up towards the halo of the Milky Way. And the colors you see on here just represent the distances to stars. They've done just a simple, what they call a color cut in their measurements. And what comes out is basically the distances to the stars. When we look at how the stars in the halo of the Milky Way are ordered, you don't find that they're just random, buzzing around in a nice regular sphere like the earlier picture suggested. You actually see that there's trails cutting right through the halo of our galaxy. And what we think has gone on here is that over time, the Milky Way galaxy has interacted with other galaxies. This is how astronomers think galaxies grow, is by gobbling up smaller galaxies. And so what happens is when a smaller galaxy gets gobbled up by a big one, it gets torn apart into tidal tails. And what we have here is streams of tidal tails stretching through the halo of our Milky Way galaxy. So this by itself, a very simple graph to make, shows very convincingly that the Milky Way has demonstrably gone through accretion events in the past, and those are imprinted as like jet contrails through the halo. Now, like I said, a halo is just a trace component stellar-wise. If you just count the number of stars, there's not very many stars that are actually in the halo. Most of the stars are in the disk where we live, but the disk is also a much more busy place. There's giant molecular clouds in the disk, star formation. Most of the star formation going on in the Milky Way now is occurring in the disk near the plane of the disk. There's structures in the disk like the bar, which can cause stars to get on weird orbits. There's clusters of stars in the disk, which might be evaporating to produce strings of stars like this. So although we expect, if the accretion scenario is the right way to think about how our galaxy is grown, which is pretty well demonstrated here, we ought to be able to find those same kind of things in the disk of the Milky Way as well. But it's a much more difficult problem. And so my PhD dissertation is looking for the same kind of signature, evidence of past accretion events that are actually in the disk of the Milky Way, not in the halo where it's a much simpler, there's not as much to throw stars onto different kind of orbits. So people have looked for this. This was a conference paper by Anina Helmy, came out in 2006. That was one of the papers that I read early on as a grad student. They got me interested in trying to tackle this problem. What she's done here is she's taken the kinematics of the stars, how the stars are moving, and plotted them simply in terms of their velocity components. So you want to talk about the three-dimensional velocity of an object, you've got three components. You could say your x, your y, and your z, right? But if you're talking about circular motion, you're probably going to say the radius, the circular velocity, and the kind of axial velocity. So we have r, phi, and v. And so that's why you see here v phi and vr and vz. So this is just kind of two-dimensional projections of the kinematics of all the stars. Incidentally, these aren't just all the stars in the disk. These are just the ones that are nearby. It turns out that we can get our best measurements of how stars are moving for the nearby stars. So these are stars in what we call the solar neighborhood, which is only about as much as 150 parsecs from where we are. So that's just it's a little bitty bubble within the disk. But whenever we just look about the stars that are just kind of passing by us in the neighborhood, and we look at how the kinematics of those stars lay out, they're not nice ordered balls. They have lumpiness to them. So you can see there's kind of a lump there, and there's a kind of a lump there, and there's kind of a lump there. And it turns out these are groups of stars that have been known for a very long time. We've known about these guys since the 50s. There's this guy called Erwin Eggen who defined all of these groups of stars they called moving groups at the time. And these are three of them. This top bump right here is what we call the Cirrus moving group. This guy on the side is the Hyades Pleiades moving group. And then down here is what we call the Hercules moving group. So these are strings of stars, kinematically related groups of stars that are passing by us in the solar neighborhood. Amina Helmy and her work also went a step further and tried to quantify some even smaller groups within this, smaller clumps that are kind of buried in here that you can't see just with your eye. You have to do a statistical analysis in order to get those groups to pop out. So my basic data in my thesis that I worked on is basically stars that are in these three groups, Hercules, Hyades, and Cirrus, plus some special groups that Amina Helmy identified that I went to see if there was more evidence besides just the kinematics that we could say that they're distinct from the other stars in the Milky Way's disk. So this is just a blow-up. I wasn't sure if the previous slide was going to show very well. So this is just a blow-up of one of those others. So hopefully you can see the blobs a little bit different, a little bit better here. The one there, the one there, and the one here. Incidentally, this is the kind of plot that you can try to use to define what the bulk motion of stars are in the disk. You can see that if you try to draw just kind of a dot in the middle of this, and this is the circular velocity, you might think it's somewhere in there. Well, that's about 220 kilometers per second, which is if somebody says, well, how fast are we going around the galactic center? This is one way you can define that number, is just by what's the centroid of this blob. It turns out to be about 220. So this is the same graph, but now I'll put the blobs actually drawn back in there. The Hercules is more diffuse, and the color isn't very good for seeing on the screen, but it's down here. There's two groups. So we know that there are kinematically related groups of stars moving in the disk, streams of stars. What are all the different ideas we have to produce these streams? Because that's what we really want to know. If we want to talk about how the galactic disk has evolved, has changed over time, then we need to be able to connect a mechanism of formation with our streams. So, of course, our imaginations run wild, and we can come up with some different scenarios that we can imagine could produce streams. So one, this is actually the original hypothesis by Erwin Eggen back in the 50s, is that these moving groups of stars were associated with a cluster of stars which was born and then began to dissolve, and as it dissolves, the stars which escape from the dissolving cluster tend to inherit the kinematic profile of their parent, the cluster that they evaporated from. And so you can kind of expect that when a cluster dissolves, it's going to leave a trail of stars in its wake. It's kind of like how a comet, as it goes around the sun, leaves a trail of debris, and then whenever the Earth passes through that trail, we have a meteor shower. It's kind of like that. Another way that we can imagine is that whenever stars are just kind of passing through the galactic disk, if they pass by a particularly large structure within the disk, that can cause the stars to be thrown onto a new orbit, which is preferentially in some direction. And it turns out that the galactic bar is, if you read the literature on this, the galactic bar is almost always the culprit that they point out that's causing these, what they call dynamical streams. So dynamical in the sense that these stars aren't related by birth. They're related by, they just both happen to pass by the galactic bar and got thrown into the same track. And so they're all kind of just moving together just because they happen to pass by the bar. So this is kind of the dissolving cluster hypothesis. This is the dynamical interaction hypothesis. And then there's a really cool one down here, which would be the accretion event hypothesis. We know what happens in the halo. Can we find it in the disk? This is, when I started my dissertation, this is what I was really hoping to see, was accretion event type stuff. So after having said all this, how the heck do we even tell this apart? How do you know the difference between what a dissolved cluster streams versus an accretion that a string should look like? That's where composition comes in. Because it turns out that stars in the course of their lives produce different elements, and the particular elements they produce has everything to do with the mass of the stars. And if you're thinking about a whole group of stars that are kind of evolving together, things like the star formation rate ends up having a direct impact on what kind of chemical fingerprint that particular population is going to have. So there's a whole line of reasoning to get to that conclusion. The basics are here. It's that massive stars have short lives and they produce particular kinds of elements. There's one group we call the R process elements. So R stands for rapid. It's a neutron capture process. So this is whenever you have an atom sitting there and a neutron comes along and smacks into it, and then that neutron can decay. It releases an electron and a proton, or the electron and the protons. It causes the atomic number of the element to change. It changes it into a different element, and so you can get production of new elements by smashing a neutron into it and then having the neutron decay. So we think that the kind of neutron capture that produces a certain set of elements occur in core collapse type supernovas. So these are very massive stars. Very massive stars have short lives. So if you see a star with a lot of all process elements in it, you can expect that somewhere in its past it had a very massive star or a bunch of very massive stars. Likewise, there's a set of elements called the alpha elements. So an alpha particle is basically a helium nucleus. If you are burning, the only kind of stars that can produce a lot of alpha elements are also massive stars. They produce them in kind of their regular burning phase. Smaller stars just can't, they don't have the energy to produce those kind of interactions. So all process elements, alpha elements, those come from massive stars with short lives. There's other sets of elements called the S process elements. Now that's a nucleosynthetic pathway that occurs in a certain class of stars called AGB, which stands for asymptotic giant branch stars. Those occur in low to intermediate mass stars. Low to intermediate mass stars have longer lives. So the kind of elements that would come out of those kind of stars don't start to enrich the population star until later on. So there's kind of a balancing act going on here between how fast, like given a certain star formation rate, will produce a different proportion of these two elements. So a good way to probe the star formation rate of a population of stars is to take one of these guys and divide it by one of these guys. Because if it's a population made of mostly this, you'll get a fraction that's very high. And if you get the converse of that, where you don't have very much R but you have a lot of S, then you'll get a ratio that's very low. So you can kind of find a way to compositionally separate groups that say they might be in the same string, but you can separate stars that have different paths by looking at the ratios of elements which are associated with different nucleosynthetic pathways. So a lot of big words here, right? the end of the argument is that basically the composition of a star ends up being like its DNA, because the composition that you measure is telling something about the progenitors that come before it. So out of this comes the technique in astronomy called chemical tagging. It's basically having a population of stars, knowing what the chemical fingerprint of that population is. Once you've got enough of them, then you can go other places and see if you can find that fingerprint elsewhere. And then if you can find some kinematic relations between these two, you can begin to piece together how this population we see now might have been distributed some other way in the past. So here is a very busy plot. It's trying to motivate how these different populations with different chemical fingerprints are so well separated when you plot them versus their compositional, composition. So what we have here on the y-axis is, think of this as the amount of alpha elements that a star has. And then down here on the bottom, this is called the metallicity. Let's call this, in a very rough sense, the age of the star. It's not a great analogy, but for the sake of simplicity, let's think about this as age. When we make a plot like this, what we find is that the disk of the Milky Way, that's all these yellow dots right here. When we look at them, the composition of disk stars, they kind of fall down here. When we look at the thick disk, they're very close, so these kind of bluish, greenish stars right here, those are what the thick disk stars fall like. So you can see there's a chemical separation, especially between here. So this is one of the arguments in favor that the thick and thin disks really are distinct, is that they separate out according to their compositions when you make a plot like this. This huge cloud up here, well, you look at that's the halo. They're older, less what we call metallicity. And then these guys down right here are the most interesting part of this whole plot, because these stars down here, these big white dots, these come from another galaxy. These are stars in a galaxy called the Sagittarius Dwarf Spiral Galaxy. This is a small galaxy that is in the process of being torn apart by the Milky Way. So it's nearby. It's being gobbled up right now. And we can measure what the composition of those stars are. And when we look at that, it's incredibly different. I mean, this is the whole galactic disk. And when we look at stars in this dwarf spiral galaxy, it's way down here. Why would it be way down there? Remember what I said about this kind of ratio telling you something about the star formation rate? Well, it turns out that dwarf spiral galaxies, being smaller, having less gas, they have lower star formation rates. So it makes every bit of sense that there would be this kind of separation. The dwarf spiral galaxy has experienced a lower overall star formation rate than what we see in the disk. And so that's why this nice separation is. So if we wanted to find stars in the disk that we could tie to past accretion events, this is exactly the kind of signature we want to look for. We want to look for stars in the disk of the Milky Way that have exotic chemical signatures that register low on this kind of scale. And also, incidentally, you see this big star right here. This represents a particular cluster of stars called the, which one is it? Palomar 12. Before this paper came out, they weren't sure if Palomar 12 had an origin within the Sagittarius dwarf galaxy. There was some kinematic suggestions that it might be. And in this paper, they pretty much nailed it down by showing that it falls right in the trend with the Sagittarius dwarf galaxy. So this is an example of a triumph of the chemical tagging technique, because it was able to tag this guy as being part of these white dots, because it fell in right there nicely with them. So I've kind of talked about some of my dissertation already. So to summarize, I had a whole bunch of stars. It started off with about 600. These were inherited from my thesis advisor, Bruce Carney. He originally took them at the Keck Observatory in Hawaii as part of a, I'm getting short on time, as part of a planet search. So let's, and I also took some of my own data in Texas. I made software to do a spectral analysis. These are spectra of stars, and so this is one technique that astronomers can use to measure what stars are made of. I did spectra on a whole bunch of stars, and with those results, the compositional results. I cross-referenced that with kinematic information that I got from elsewhere. And then I basically did some statistics. I grouped my stars in my data set according to what group we know they fall into with what they call a Bayesian statistical method. And then I tried to do some population testing with a statistical test called the KS test. This is a way of saying, given this group and this group and what their properties are, can I say with any statistical significance that they must have been drawn from the same parent population? So this is one slide of what the spectral analysis looks like. I have measured 3 elements: europium, which is the R process element, lanthanum, which is S, and then I also measured iron because of that weird metallicity that I was showing you a minute ago in the other plot. So these 3 curves here show what changing the europium abundance by a little bit looks like. And so I basically am fitting the data as the white curve with these 3 different model curves, and the pink one right there is what a good fit looks like. And so this is basically how we get a result. It fits, it matches, so the pink line is telling me what that line is telling me about the amount of europium in that star. So this is the result of the KS test. Without getting too deep into it, the main thing that we're looking for here is a separation between these two. So the white line right here represents one population, and then the colored line, so the white line is usually going to be the test population, the big background population. In this case, this is just kind of a sanity check where I'm just comparing the thick disk to the thin disk and verifying that my program does work. It does find the difference between the thin and thick disk. So this nice wide separation between the two curves, you do your calculation and you get this thing called a p-value. This gives you the probability that they could have been drawn from the same parent population. You see I'm getting a probability of 0. 0 means no, they were not drawn from the same parent population. So this is saying that these are really 2 chemically distinct populations. This is the result from one of my tests on the stream identified by Nina Hilny, and I find a pretty good signature there. So I'm finding that compared to just any old Milky Way star, these really are different statistically. They must be different somehow. Unfortunately, the sense of this is not in the same sense that we would like to expect for a accretion event. This is pointing more towards sampling a different part of the galactic disk. So this is actually, this is the side that it's on, is looking more like a difference between thick disk and thin disk. You see the separations on the same side. So the Helmy stream, unfortunately, looks like it might just be a dynamical stream within the thick disk. So that was kind of a letdown when I got to that conclusion, my dissertation. But you don't know what you're going to get. You just got to try and see what you get and go with what the data tells you, and that's what the data told me. Also went ahead, because, I mean, first I did this and found that it wasn't a really exciting result. So I also did the same thing on the classical streams, those big blobs that I showed you earlier, to see what kind of result I could get from them. And so I've got, at the height of these streams, see how nicely these lie on top of each other. Part of this is just because I have very low number of stars in the group. It turns out that in order to be able to distinguish the 2 populations, you also have to have a lot of stars to compare against each other. And since this one is just 11, you can see they fall right over each other, which is telling you that you can't distinguish between the 2. This doesn't necessarily mean that these are the same population, because the KS test doesn't tell you that. All this tells you is that with these data, you can't tell the difference. There's actually a good reason to believe that these may actually be different, because the Hyades cluster actually is in there. And other people have found evaporated members of the Hyades cluster elsewhere in the stream. So according to Egan's original hypothesis from the 50s, this may be the one that comes the closest to satisfying that, although my work doesn't have enough of the stars to really support it on its own. The Hercules stream, p-value of 0.03, so I'm getting kind of a signal here. The Hercules stream, when you look at the kinematics of the stars in the Hercules stream, they look like thick disk stars. They were the guys that were the diffuse one down in the corner. So the Hercules stream has kinematics like the thick disk, and whenever we look at the specific trajectory that that stream seems to be on, other people say that it looks like it was produced by a dynamic resonance with the galactic bar. So this one seems to be a dynamical stream as well. Why would the chemical difference be there? Well, it's because these stars are coming from the inner disk. So the signature here isn't interpreted in terms of an accretion event or anything exciting like that. This is just sampling a different part of the disk because we know that the inner disk had a greater star formation rate than what we have out where we live. So we think these are just travelers from the inner disk that look a little bit different from where they're from. And the Cirrus stream is also really interesting, but especially interesting because of all my groups. It's the only one that has the signal on the other side. This is finding a R process enriched group. And it also turns out that it may share a dynamical origin with the Hercules stream, in spite of the fact of having a different compositional signature. That was kind of at the end of my thesis left as one of these future work things, was to take a closer look between these two and see if there's any chemical similarities when you look even closer. So I think that's about the end of my talk. There's my conclusions. Did I leave anything out? Nope. Okay, so thank you very much. So, questions? Yes. The big busy one? Whoa. So my slides seem to have gone down. Well, the laptop's still showing it. Okay, we're back. So the white dots here, so we can see the body of the Sagittarius dwarf. It's spatially distinct from ours. It's close by, but it's spatially distinct and it's ripped into these tails. And we actually can get spectra of those stars within the body of the Sagittarius dwarf. And those white dots are what we see. So these are stars. Well, the yellow dots in any case, but they're kind of scattered through here. Those are stars that are kinematically disk stars. They're nearby. These are actually dwarf stars, dwarfs and subdwarf stars, dwarfs and subgiant stars. These guys are all giants because they're farther away. They got to be giants for us to be able to get data. So we come to this plot kind of already knowing in advance that these are stars from another galaxy, because we see them actually in the other galaxy. The triumph of chemical tagging is this star, right, this big star. So they're showing us a big icon here because it's actually the average of several stars. It's a cluster of stars called Palomar 12. And so we knew for a long time before this work that Palomar 12 was weird. But we didn't really know how weird, and we didn't know why it was the way it was. It doesn't really fit into our picture of how the other globular clusters are. And it turns out one group did some kinematic studies and found that it was plausible that Palomar 12 had a kinematic track that would have led back to the Sagittarius dwarf. And so there was a follow-up study to try really hard to get the spectral data to make the composition analysis, and bam, there it is, right in the body. So the triumph is seeing that this star lies with the white dots, and we already knew the white dots were Sagittarius dwarfs, so it's hard to debate against that. Yeah.
So there's a magnetic stream, and we're really confident that those are streams of stars that from other galaxies.
Mm-hmm.
So is there any work that's been done that would use them as a control to compare your other stars that you're kind of observed and see up there, similar to one of those stars in the Magellanic Street, versus the ones that are in your host Milky Way?
So the green dots you see here, these are studies from other local group dwarf spheroidals. So this is one dwarf spheroidal. When we look at other dwarf spheroidals, we get numbers like this. So they might have a different metallicity, but we always find that they are offset downward from Milky Way type stars. So when I'm looking at my string to see if they are the kind of exotic stars that I'd like to see to make any kind of claim on an accretion event, would be to find a very depressed measurement of a fast to low star formation rate element. So here's this is alpha elements in iron, but I did europium to S process. I would be looking for that same kind of clear separation. But the numbers that I got are much more in agreement with just Milky Way trends. Still, it's a result, but it's not as exciting as I hoped.